Hello everyone, my name is Farivar Rajabi, a first-year PhD student at Toronto Metropolitan University. I'm presenting advances in data-driven fault detection and diagnosis for HVAC systems, a review of recent developments. The subject can be looked at under the following headings: introduction, significance of the study, overview of relevant literature, the gaps, methods, discussion, and next steps. Building systems, including heating, ventilation, and air conditioning, or HVAC system, which is actually the heart of each building, are usually subject to faults, and these faults can lead to undesirable performance like excessive energy waste, high maintenance costs, and uncomfortable indoor environment, and poor indoor air quality. And these faults refers to sensor failures. For example, temperature sensor fails and starts giving incorrect readings, equipment failures, which is failure of physical components. For example, the compressor in an air conditioning unit fails, or faulty system operation. For example, the control system is not properly programmed. And after that, the system keep the air conditioning running even when the building is unoccupied. So let's see what report says. Studies have shown that 15 to 30% of energy may be wasted due to building system faults and improper controls. So we need to do something to solve this problem, and we call it fault detection and diagnosis. To be specific, fault detection is defined as determination that the operation of the building is incorrect or unacceptable. And the fault diagnosis is identification or localization of the cause of the fault operation. Once again, let's see what report says. It is reported that FDD users in the office and higher education market sectors of the United States were able to achieve 10% median energy saving annually with 2 years simple payback period. So it's a good investment. We can classify FDD methods into data-driven and knowledge-driven and also hybrid methods. Data-driven are those that are built and trained from the data via machine learning techniques like classification, unsupervised learning, and regression. So we have a building automation system, we have data sensing, and we have machine learning. So we can adopt data-driven FDD for our buildings. On the other hand, we have knowledge-based methods. We can create a physical model of the asset to see what is the ideal operation of the system. And rule-based methods, it's like if the outside temperature is below than 20 degrees, then the air conditioning compressor should not be running. And something we prefer to tune the parameters of our model with process data. So this is going to be the hybrid method. And the main reason that we are interested in data-driven FDD methods is that they need a little or no prior knowledge and has the potential to achieve high detection and diagnosis accuracy. The first step for FDD is the data collection process. Data collection, it can be done with the BAS, Building Automation System, meters, or other data source like Internet of Things. The problem is that each building may have its unique BAS, or Building Automation System configurations, or unique database structure and data point naming. So we need to use a standard communication protocols like BACnet system and metadata schema like project haystack and brick. And these protocols is the data collection process. After that, we need to do some sort of data cleansing. For example, we need to impute some missing data with methods like filtering, or expectation maximization algorithms, or we need to detect and filter out outliers. After that, we probably need some additional pre-processing like feature selection, data reduction, data scaling, because we don't like to work with the data with high-dimensional data. Filter, wrapper, embedded, and hybrid methods are some example of data reduction techniques. For real-time implementation of FDD method, we need to compare incoming data or snapshot data with a baseline. And baseline represents normal operation of the system or ideal operation of the system. And this baseline can be generated by simulation or created from historical data. And of course, the situation of the baseline should be similar to the real asset to make sure that they are in a similar operation mode, like outdoor weather conditions and internal load profile. And the final step is to fault detection and diagnosis. We can categorize fault detection as supervised, semi-supervised, unsupervised. Supervised method for fault detection are trained using normal operation. We need to have labeled data. And this method can be further categorized into classification or regression. Using classification, we can predict whether the incoming data belongs to the fault class or fault-free class. And regression can predict the system operation status, which is then compared to the baseline. And any residual or difference between the baseline would be residual and would be indicative of faults. A big challenge with supervised method, as I said before, is obtaining sufficient label data for training the models. So it's not possible to apply it in real buildings. And most of the studies applied it into simulation data and actually published data with the ASHRAE that was published for the evaluating the proposed methods. Alternatively, semi-supervised methods are more suitable when we have only limited label data. Semi-supervised method can transfer unlabeled data to labeled classes by comparing the incoming data with normal operation. And it can iteratively update the training data set to make the data set larger. Although semi-supervised can perform better when limited label data is available, these methods have higher computational cost than supervised learning. And lastly, unsupervised methods do not require labels. So these methods are helpful for discovering the hidden correlation between the data and the data point that we get from the BAS, like clustering and principal component analysis. So the problem is not solved yet. A few days ago, I was running a very basic clustering algorithm on my data set, and I reached to 46% accuracy. So it means if a facility manager sits at the table and flips a coin, he has a higher chance of detecting the fault. So we don't need to hire data scientists to develop such algorithms. We can categorize fault diagnosis to inference-based and classification. Bayesian network is an inference-based algorithm. By Bayesian network, we can establish a probability-based relationship, actually table between our variables. And if we have any evidence, if we have any symptom of fault, we can see the probabilities of presence of fault in any variables that we have. And also we have fault tree, which is similar to actually if-then rules. And again, we have classification, which has the challenge of having labeled data. There is a more advanced approach, fault prognosis, which is the process of predicting future system states, especially predicting the occurrence of fault before it happens. So we can realize how much time is left before a failure is expected to occur. And this method will enable us to correct the faults before they cause system failure. In terms of system studied, HVAC fault can be categorized as hardware, software, and by the type of component. Excuse me. Okay. Hardware faults further include equipment fault, sensor faults, and control device, including actuator. Software faults further include controller faults. For example, there is an issue with the control algorithm. Human fault, when the person who is operating the system make a mistake, and control logic error like programming errors. And the detection of these faults can be implemented at the building level, system or subsystem level, like air handling units, and component level, like damper. The main difference is that we look at different sources of data. In building level, for example, we mainly focus on energy trends in order to detect non-optimal operational patterns, and we monitor overall performance of the building, like energy usage. The data can be supplied from a simulation, laboratory experiments, and field measurements from real building. Among all these reviewed studies, the usage of lab experience were the most, and the majority of whole building applications rely on real field measurement data, and system level mainly rely on laboratory data. And simulated data can be also generated from simulation softwares like Transys, Energy Plus, and HVAC. In terms of, in terms of challenges and opportunities, real building deployment, first of all, real building deployments are challenging mainly because of incomplete information and uncertainty of the data. Secondly, there are limited studies that compare the performance between FDD methods, especially under different categories like data-driven vs rule-based, supervised vs unsupervised. So more comparison studies are needed to demonstrate the performance of data-driven methods. Another challenge is scalability and transferability. I mean, different buildings may have different situation in terms of HVAC system design, weather, and occupancy, so data-driven FDD methods, which is developed for one building, may not be applicable for another building. In order to improve the scalability and the transferability, the use of hybrid approaches and transfer learning is recommended. And lastly, for the market, interpretability of the FDD methods is, which is the ability to explain how fault is detected or diagnosed, is very important. As a final concern, building automation system are typically connected to the internet, so they're going to be potential targets to cyber attacks. So we need to take cybersecurity and data privacy into account. As acknowledgements, NSERC, Fuse Forward, and Toronto Metropolitan University Facility Management are supporting our studies. Thank you very much.